Welcome to the next lecture on phase diagram. The previous lecture we were more focused towards atoms, arrangement of atoms, the atomic packing factor, coordination number, and what are all the Bravais lattice, 7 different types of Bravais lattice. We were trying to understand more from the atomic or at the microstructural level. Now, let us try to move towards different phases. What will happen when a same metal is taken to a higher temperature? It gets into liquid phase, then it gets into a solid phase on curing. So, this is also an important lecture when we try to understand the processes in future. In this lecture, we will try to have an introduction, then there are several phase diagrams, but we will try to categorize into 3 simple and try to take unary phase, binary phase type 1, binary phase type 2. Iron carbide diagram is a most popular phase diagram which is being used in academia. So, we will try to see iron carbon diagram, then iron carbon structures. Finally, we will try to have a recap. If you look at this graph, you will try to see there is a overlap of information with the graph which we saw in the previous class. Volume divided by unit weight with respect to temperature. You remember that, where in which we had a sharp change in the melting point, right. So, the same curve when it is plotted with respect to temperature versus time, for a pure metal you will see the response like this. So, the melting point starts here, right. Above this, when you try to take to a higher temperature, the metal will be in liquid form. Then after this point, it starts solidifying. When it starts solidifying, you will have liquid plus solid. When it crosses the freezing end, it becomes a solid. So, now liquid phase, you will not have much of crystal structure and other things discussion, but once it enters into a freezing beginning to freezing end, you will have a mixture of liquid and solid. When we try to make sugarcane syrup, when you try to make a sugarcane syrup, you will try to see as and when it solidifies from liquid to solid. So, basically how do you make a sugar syrup? You take a solid sugar, add water to it, boil it. Moment the water gets boiled, the sugar gets diffused, and then what you have is you have something like a viscous material. When this viscous material is allowed to solidify, it will have a mixture of liquid and solid. You would have seen on the skin on the top, right, liquid, something like that, a solid will be floating on a liquid. So, a similar thing will happen when it tries to solidify. So, you will try to have liquid plus solid. So, now what are the phases which happens there and how is it going to bring a difference is what we will try to see. So, this graph is for a pure metal. When you have an alloy, you will have something which is, you will not have a sharp response, but you will have something like this response. Right, the melting point, you will have a zone, not like a discrete point. The term phase describes an homogeneous mass of material, such as metal in which the grains are the same crystal structure. For example, in brass, zinc is dissolved in copper. Okay, this is an alloy. So, the phase describes any homogeneous mass of material, such as metal in which the grains all have the same crystal lattice structure. The phase diagram. So, this temperature versus time, this we will try to see is a phase diagram. A phase diagram is a graphical representation that shows what phase exists in the material system at different temperature and when the system is made up of different elements or compounds. Phase diagram, you will try to have temperature versus time. What are all the different phases which are getting formed? A phase diagram is a graphical representation that shows what phase exists in a material system. Material system, we saw brass, wherein which you have zinc plus copper. When the system is made up of different elements or compounds. A phase diagram, also called as equilibrium or constitutional diagram. So, phase diagram is sometimes called as equilibrium or constitutional. Why is it said constitutional? We will try to see solid, liquid, what are the phases coming there. Shows the relationship among temperature, composition and phase present. Why composition is important? Because if let us take an example of carbon and iron. Now, what is happening at the carbon atoms are small, the iron atoms are large. When you see the unit cell, the carbon atoms diffuses into the unit of iron. So, that is what amount, that is what is the composition. So, at various temperatures, composition and phase present in a particular alloy system at equilibrium will be seen from the phase diagram. We keep on repeating the term called as equilibrium. What does equilibrium mean? Equilibrium means that the state of a system remains constant over an infinite period of time is called as equilibrium. The state of a system remains constant. The state, right? The state of a system. The constitutional indicates, the constitutional diagram indicates the relationship among the structure, composition and physical makeup of the alloy. So, understanding phase diagram is very, very important because it is going to give you time, temperature relationship for different elements. And then it also tries to tell in a particular alloying system, it tries to say. Then constant over an infinite period of time. Unary phase diagram. This is a very famous phase diagram wherein which you take ice, gets converted or gets converted into water, then that gets converted into steam. The x-axis is temperature. So, you have Tp, triple point here, and you have Tc, a critical point here. Okay. So, this is pressure. So, ice, as and when you increase the temperature, solid becomes a liquid, that liquid becomes a steam. Ice, water, steam. So, if you see that, there is something called as a triple point. So, this triple point is always very important because we try to play with pressure. So, it is mainly used to show the phase diagram of water or any other pure metal or material. They are very limited, practically utilizes of such diagram plotted between temperature and pressure. Because when you change the pressure also, water gets converted into steam. So, this is just an example, or this exists only for water and some other pure material. We always very seldom we use it from the materials perspective from the manufacturing point. Binary phase diagram. Binary phase diagram means there are two components, there are two. These diagrams are further divided into three categories. The material which are completely soluble in liquid as well as a solid state. So, liquid. So, here it is olivine solid solution. So, here it is solid solution plus olivine solid solution plus liquid. So, here it tries to talk about temperature with respect to some percentage. So, the material which are completely soluble in liquid as well as in solid state. The material that is completely soluble in liquid state, but partially soluble in the solid state is called as eutectic phase diagram. So, here it will be completely liquid, here it will be completely in a solid. So, here it will be liquid plus solid. The material which are completely soluble in liquid state and completely insoluble in solid state. So, you can exist in 3. So, type 1 in binary phase diagram, type 1. So, temperature versus composition we have taken. So, here we are trying to take copper, here we are trying to take nickel, right. So, nickel weight percentage is seen. So, nickel weight percentage 20 means 80% is copper. If it is 80 nickel means 20% is copper. So, we are trying to understand at what temperature, what composition, what are all the microstructure phases you can see or microstructure you can see. The material which are completely soluble in liquid as well as in solid state. The line that separates the liquid phase from that of a mushy zone is called as a liquidus line. So, this line is called as a liquidus line because it is liquid, and then at this line it tries to distinguish itself into liquid plus alpha, right. And this is the start of the mushy zone. The end of the mushy zone, what you get is a solidus line. So, inside this mushy zone, you will always have liquid plus solid. So, the liquid is L, solid is alpha, then L plus A is the mushy zone, L plus alpha, right. So, at varying temperature we know, for example, I can try to take a 20%, you will have 20% around about, when the nickel is 20%, around about 1200 or 1150 or 80, if you try to heat it, it will form a liquid. And when it goes around about 1120 or 30, you will see the solidus line getting formed. When the composition changes, you see the temperature offset happens, and you can see the mushy zone also tries to form. The line that separates the mushy zone from the solid phase is called a solidus line. On such a phase diagram, solidification takes place over a range of temperature. This is what I said, solidification takes on a range, because in a pure metal it will be a straight line, one point, but here it will be a range. So, when we try to take a binary phase diagram 2 type, so you can see here like solid, this is the liquidus line, this is a liquidus line, right, and this is a solidus line. This is a solidus line, right. So, from here you can see solidus, and then you can see up to here, right, and solvus you can see here, right. At above the liquidus line, you have a liquid form. Below the solidus line, you have a solid, right. So, let us now look into detail. So, you have a temperature in the y axis, then you have tin percentage changing, this is lead. So, tin percentage changing. So, that is in the x axis. The material which are completely soluble in the liquid state, but partially soluble in the solid state is called as eutectic phase diagram. I repeat, the material which are completely soluble in the liquid state, but partially soluble in the solid state is called as eutectic phase diagram, and it has a eutectic point also. The alpha phase is the solidus solubility of tin in lead, and beta phase is the solid solubility of lead in tin. So, you can see here alpha, beta. So, in binary phase diagram 2, there appears a point at which liquid converts into two different solids. So, the reaction is called as eutectic reaction. So, liquid on cooling leads to solid 1 and solid 2, which is alpha and beta. While heating, it gets back into this. This reaction is invariant in nature and appears at particular temperature and composition. There are three phases: alpha phase, beta phase and liquid at the eutectic point. Where is the eutectic point? This is a point. Liquid leading to two solids, eutectic. When we go to type 3, so we try to take cadmium, we try to take bismuth. So, temperature versus composition. You can see here the material which are completely soluble in the liquid state are completely insoluble in the solid state. So, you can see here there is a liquidous line, there is a liquid. So, liquid plus bismuth, liquid plus cadmium, right. So, they have a solidus line. So, below this line they will have Bi and Cd mixture. So, the material which are completely soluble in the liquid state and completely insoluble in the solid state. Now, let us move to iron carbide diagram. Pure iron upon heating experiences two changes in crystal structure before it melts. At room temperature, the stable form called ferrite or alpha iron has a BCC structure. So, as and when the temperature goes high, the crystal structure also changes. The ferrite experiences a polymorphic transformation to FCC austenite or gamma iron at 912 degrees Celsius. This austenitic persists to 1394 degrees Celsius, at which temperature the FCC austenite reverts back to BCC phase known as gamma ferrite, which finally melts. So, now let us try to understand iron carbide diagram in detail. So, in the x axis you will try to have iron plus carbon. So, it is 0% carbon, here it is 6.7% carbon. So, we have seen in the first week itself that up to 2.1% approximately, if you have iron plus carbon, it leads to steel. Anything above 2.1, it will lead to cast iron. So, cast iron will have more amount of carbon and steel will have less amount. And here we again saw low carbon steel, medium carbon steel and high carbon steel. Again, depending upon the proportion of percentage, this can change. Now, let us try to understand what are all the different phases which are there. You have austenite, gamma. So, if you look at the microstructure, you will see there is a gamma phase. When this gamma is mixed with a liquid phase, right. When you try to solidify, from higher temperature, it is coming down to lower temperature. Now, we are trying to look at a microstructure at this point. So, you will have a gamma phase. When it is trying to slowly cool down, right, if you see here along with the gamma phase, you have Fe3 Fe3C also present. And further, when you cool down, you will see here there is pearlitic structure where Fe3C in the eutectoid and pro-eutectoid portion are seen. We will see eutectoid and pro-eutectoid quickly. So now when you see there, as and when the solidification happens, you will try to get a pearlite and a cementite structure. Now let us try to drop down. See here, this portion, when you move towards 0, it forms hypoeutectoid. When you move from 0.76 towards 2, it forms hypereutectoid. We have seen what is eutectoid. So now at 0.76, you drop down, you see a gamma phase which is already here. Then when it goes down, you will try to see alpha plus, you will try this alpha what you saw here, alpha plus Fe3C. When you try to cool down and drop a line in the hypoeutectoid region, you will try to see at 912 degrees Celsius, you will form gamma phase. Then when it slowly cools down, you will have alpha plus gamma. What is gamma? Gamma is austenite. So if you want only gamma phase, you just have to take the composition and drop down the temperature at this point. You will get only alpha ferrite. Right? When you do exactly here. So when we try to do at this portion, you will try to get, see, you will try to get ferrite plus pearlite. When you try to do it at this point, above the start of hypoeutectic or in the hypoeutectic region, you get pearlite plus cementite. So you get ferrite or you get cementite. Pearlite plus ferrite or pearlite and cementite. So if you see here, you will try to see how is the microstructure getting formed. You can see here Fe3C and you have eutectoid alpha there. And this structure is pearlitic structure, and you have an intermediate which is called as hypoeutectoid alpha. So eutectoid alpha or hypoeutectoid alpha. So in this diagram, you can try to see by changing the composition of carbon in iron, you try to get varying compositions. So if you look at this zone where gamma and Fe3C are there, you have cementite and ledubarite getting formed. When you try to see at this portion above A1 and AC critical at this portion, you have austenite, ledubarite and cementite getting formed. When it goes down below the temperature of 800 degrees Celsius, you get alpha plus Fe3C, and at 0.67 you get this Fe3C. So you see here at this point you get alpha plus you get Fe3C, which is cementite, pearlite and transformed ledubarite will be there. So in this diagram, it clearly talks about iron carbide with varying phase and composition, what all different types of microstructures can be formed. So these are the two reactions, eutectic reaction and eutectoid reaction. In eutectic reaction, you will have a liquid leading to gamma plus Fe3C. When it is cooling, you will get gamma plus Fe3C. When it is heating, you get into liquid. When you talk about eutectoid, you will see gamma forms alpha plus Fe3C. Right? So the difference is this. So in eutectoid, it is a reaction when a liquid phase converts into two solid phase. At 1147 degrees Celsius and 4.3 degree at 4.3% of carbon, you are called as eutectic temperature and eutectic compositional respectively. So you look at the temperature, look at the composition, right? When you talk about eutectoid at 723 degrees Celsius and at 0.76 composition, what you get is a eutectoid temperature and a eutectoid composition. So, eutectic and eutectoid can be clearly seen from this phase diagram. There is peritectic also getting formed in this diagram. It is a reaction when a liquid phase and a solid phase converts into one solid. So, liquid plus solid converts into one solid. It is called as peritectic reaction. If you go to this diagram, you can see eutectic, peritectic. So, the microstructure generally which are formed in iron and steel diagram are alpha ferrite, cementide Fe3C, austenite which is nothing but gamma, the delta is ferrite. You also have a pearlite which has an alternative of alpha and Fe3C is called as pearlitic structure, and you also have ledubarite. These are some of the microstructures which are formed. Now, you can clearly understand if I wanted to change the composition, if I want to change the output what I want, I can change with respect to the composition what I add and at the respective temperatures. So, let us look at the microstructure, then you can understand more, because here what we showed was a schematic diagram. So, here let us see in little more details. So, alpha ferrite, in the BCC alpha ferrite only a small concentration of carbon are soluble. The maximum solubility is 0.02 weight percentage at 727 degrees Celsius. If you do below that, nothing is going to happen. Even though present in relatively low concentration, carbon significantly influences the mechanical property of ferrite. So, you can see here these are alpha which are there, right. So, this particular iron carbide phase is relatively soft, which make it used for magnetic application at temperatures below 768. So, below that temperature this carbon gets diffused. So, now this material can be used for magnetic properties. When we try to look at cementide Fe3C, so what are they? These are the phases which are their alpha phase. Then we are now trying to see the cementide phase. Fe3C formed when the solubility limits of carbon in alpha ferrite is exceeded below 727 degrees Celsius. It forms this cementide phase. Cementide phase are hard phases. Mechanically, cementide are very hard and brittle. So, if you see, if there is a soft material and a hard material, if there is a crack, this gets arrested. And when there are hard, so it is also brittle. So, you do not have so much of ductility. So, the strength of the steel is greatly enhanced in the presence of carbon. Cementide is also is only metastable, that is, it remains as a compound indefinitely at room temperature. So, if you want Fe3C, if you go back to this diagram, you can try to take Fe3C alone and then try to get it. So, you get cementide. So, for example, cementide. Now, let us look into austenite. FCC structure where more ductility and formability is there, which is always gamma, austenite is present. On cooling below 723 Celsius, it starts to transform, transforming pearlite and ferrite. It tries to form gamma. So, 2 trying to form gamma, right. So, this is what we are trying to see here. 2, it is normally not stable at room temperature, but under certain conditions, it is possible to obtain austenite at room conditions. They are all non-magnetic allotropic of alloys. If you want, you can try to get austenite, but you have to do some amount of changes in the heat treatment to get austenite. So, alpha is ferrite. Alpha ferrite is virtual the same as alpha ferrite, sorry, gamma ferrite. Delta ferrite is virtually the same as gamma ferrite, except for the range of temperatures over which it exhibits. Delta ferrite is stable only at relatively higher temperatures. It will have a BCC structure. The delta ion does not become magnetized. Pearlite, which is again a microstructure, carbon diffuses through the lattice structure and produces alternative plates of alpha and and cementite, that is pearlite. So, you can see from the figure very clearly. Pearlite, the structure is also called pearlite and it is produced by diffusion. Pearlite is not a phase, it is a mixture of alpha plus Fe3C. The thick light layers are the ferrite phase and the cementite phase appears as thin lamellae, most of which appears as dark. So, you can see here dark which is there are there. The pearlitic has properties intermediate between those of soft and ductile material and hard and brittle phase material. This is ledubarite. It is the eutectic mixture of austenite and cementite. Around 4.3% of carbon, it is formed at 1147 degrees. It is of layered form of and found in cast iron, which is responsible for better castability in cast irons. These ledubarite, black, these are all carbon which are there, which is used for lubrication. Hypoeutectoid steel, when the steel with 0.83% of carbon is cooled slightly below the eutectic temperature, austenite undergoes a phase transformation, right. It decomposes into a mixture of ferrite and cementite through a process called as diffusion. So, hypereutectoid you can see here, when the carbon percentage is 0.83. So, it should be somewhere here, is cooled, you get this. So, gamma you get this, you get eutectoid. So, when we talk about hypoeutectoid steel, so we are trying to talk about hypoeutectoid and then we are trying to talk about this is 0.83, 0.83 hypoeutectoid. When we are trying to talk about hypereutectoid, it is formed, the hypereutectoid steel, the proeutectoid cementite appears along the grain boundaries as the temperature decreases. So, this is what it is. So, in this lecture, what we saw was, we saw what is a phase, what are the different types of phases, iron-iron carbide diagram and different compositions of iron-iron carbide diagram to form microstructure of steel. Now, there is an assignment which I would ask you to go through. So, you read iron-iron carbide diagram in detail and now you will try to write down the mechanical properties, physical properties of different phases of material and see what is the relevance or understanding with respect to the microstructure and mechanical properties and physical properties. These are the references which we have used in preparing the slides, and thank you so much.